So in this video, I'll take you through how to use Gaussian elimination in solving systems of equation in which there will be a case where you get solutions, and there will be a case where you get infinitely many solutions, and a case where you get no solution. Okay. Alright, so let's start. So with this system of linear equations given, if I want to write this in Gaussian elimination, or if I want to write this in a matrix form, then I have to first write my matrix like this, open a square brackets like that, because we are dealing with three unknowns. Okay, and the first coefficient here, you write this as your first entry. It comes to the second coefficient of x2 in the same equation. So equation 1, you pick them and you write everything. So this is negative 2x1, so you just write negative 2. Comes to x2, there is 1 attached to it. Okay, then x3 is what? Negative 1. Alright, then you go to equation 2, you have x1 being 1, x2 is 2, x3 is 3. Okay, 3x3. And you come to last equation, you have 3x1, but there is no x2, so 0x2 and 1x3. So after writing this for your matrix or your equations, this is what we call the coefficient matrix. Okay, so now with this, then you bring a slash like this to differentiate between the matrix or the coefficients of the variables and the product. So we come and write these at this side. So you have 4 in the first equation, you have 13 in the second equation. Okay, 13 in the second equation. Okay, and you have 1. Okay, like that. So after writing it like this, what you do is you then come and then make sure that you perform your Gaussian elimination. Okay, by this we said that always is better if you can make a pivoting element, that is a row that should start first, and this time it should start with what? 1. By looking at the first row, second row and third row, if you see the second row is starting with 1, so we swap row 1 and row 2. Okay, so what you write is row 1, okay, and row 2, you swap them. Okay, if you swap them, then this is what you get. We get something like 1 2 3 negative 2 1 negative 1 3 0 1. Now when it comes to the column vector given, that one to swap. Okay, we get something like 13 here, 4 and 1. Okay, this is what you get. So having this, then we start performing our Gaussian elimination. Okay, so you perform your Gaussian elimination based on these metrics, but whatever you do in these metrics, it will affect the ones here. Okay, I hope you get it. I said you perform your Gaussian elimination based on these metrics. Whatever you do, it has to also affect these ones. Okay, alright, so let's go ahead and then start performing our Gaussian elimination. Okay, so in this means that if I'm to perform my Gaussian elimination, then like we did in our first video, we said row 1, okay, plus, sorry, let me write it well, it should be something times row 1, because you just reduce it based on these values here. Okay, so you stand on row 1, make sure that the value down, everything down row 1 becomes 0. Okay, actually it is under the first entry in row 1. Okay, so with this we said 2 times row 1. Okay, because 2 times 1 is 2, then plus row 2 should produce a new row 2. Okay, and looking at row 1 and row 3, what we can say is 3 times row 1 minus row 3. Okay, minus row 3 should give us a new row 3. Okay, now let's come back to our new matrix. A new matrix that will be formed is row 1. We didn't change anything in row 1, so row 1 1 2 3, then come to 13, and we are saying 2 times row 1 plus row 2 should give us a new root 2. Okay, so we are coming to deal with this. 2 times root 1, 2 times 1 will be what? 2, plus negative 2 we get 0. Okay, alright, then 2 times 2 is 4, plus 1 you get what? 5, and 2 times 3 is 6, plus negative 1 you get what? 5. Now you come to the 13 aspect. 2 times 13 is what? 26, plus 4, and we get what? 30. Okay, alright, then we come to the third row. We are saying that 3 times root 1 minus root 3 should give us root 3. Okay, and so 3 times root 1 is what? 3 times 1, that will give us 3. Okay, minus root 3, so minus the first, and so it's like 3 times this minus this, 3 times this minus that, 3 times this minus that, 3 times this minus that. Okay, that's the same thing we did for the root 2 and root 1. Okay, alright, so 3 times 1 minus 3 is what? 0, and 3 times 2 minus 0, 3 times 2 here minus 0, that is 6, minus 0, that is 6. 3, 3, 9 minus 1 is what? 8. Now 3 times 13. Okay, so you pick your calculator and punch 3 times 13, that is 39. Alright, okay, so 39, then minus 1. Okay, so 39 minus 1, and that will give you what? 38. Okay, so this, then you divide it like that. So what can we do? We are done with the first row, reducing it down. Okay, so if you want to reduce the second row, you pick this one as your pivoting row. But then looking at the second row, if you see that 5 can divide everything in second row. Okay, I hope you can see that. If that is the case, then let's say our root 2 should then be equal to, or let's do something here. Okay, or 1 over 5 root 2 should give us a new root 2. Okay, if that is the case, then we'll get a new matrix like this: 1, 2, 3, then 13 is there, then we get what? 0, 1 over 5 times everything in it, so we get 1, and we get 6. Okay, because 30 divided by 5 is 6. Okay, and now I forgot to add something. When you look at root 3, 2, you will see that 2 can divide through all of them. Okay, yeah, 2 can divide through all of them. So if you divide through, so this one to 1 over 2 row, let me write it in a different way so that you see. Okay, let me use a red pen for you. So root 3, okay, over 2 should give us a new root 3. Okay, alright, so in this, it means that my root 3 is also 0, then here will be 3, here will be 4. 38 divided by 2, okay, you get 19. Okay, like we said in our first video, we said that doing Gaussian elimination, you can multiply, you can also do what? Divide, you can change a whole lot of things. Okay, so let me erase this side for us to be able to solve the rest. Okay, now we are done with the first row. We've been able to reduce the elements under the first row. Okay, so the next question is, we are supposed to make sure that we reduce the elements under the second pivoting element. So you pick this one to be your second pivot. It's like you are going diagonal like that. Okay, so you pick this one first, you reduce it down, then you come and pick the next diagonal element, you reduce it down. So if it was, let's say, 4 by 4, you do till we get to the last one that has no element under it. Okay, so looking at this, we can say that comparing this and this, okay, we want to reduce the numbers, the number under 1. Okay, so comparing the two of them, you can say that 3 root 2 minus root 3 should give us a new root 3. Okay, should give us a new root 3. And now we get something like this: 1, 2, 3. Our 13 is still there. Okay, and we have something like 0, 1, 1, 6. Okay, we are not changing it. The only thing we are changing is what? Root 3. So 0. And now 3 times root 2. So 3 times 1 will give us what? 3. Minus 3 we get 0. And 3 times 1 will give us what? 3. Minus 4 we get what? Negative 1. And 3 times 6 is 18. Okay, minus 9. So 19. Sorry, 3 times 6 is 18. Minus 19 you get what? Negative 1 again. Okay, so this is how it goes about. Now we can divide through the whole of this root 3 by negative 1, since we have negative. So negative 1 times root 3 should give us a new root 3. Okay, now in this case should give us a new root 3. So now in this case it means that I want to make sure that the elements inside root 3 are all positives. Okay, so it means if we apply this rule on it, then we get something like this. Okay, 1 2 3, then our 13 will come, 0 1 1 6, and 0 0. When we multiply negative 1 through root 3, we get 1 1. Okay, now what this means is that since we've been able to reduce this matrix to this, it means that if you want to get our equation, okay, you want to get this equation, this whole equation back in terms of this matrix, it means this is how the statement means. You take the coefficient matrix that if you reduce 1 2 3 0 1 1 0 0 1, okay, then multiply by x1 x2 x2 x3. Okay, and this should give us 13 6 1. So the new reduced form of the last one, the constants. Okay, that is what we get. Now with this it means that if I'm to do matrix multiplication between this and this, it means 1 2 3, the first row multiply the whole column x1 x2 x3. So it means I'll get x1 plus 2x2 plus 3x3, and we are saying this should be equal to the column vector here, so or column matrix there, so it becomes 13. The first entry should be equal to the first entry in both sides. Okay, now this second row times this whole column will give us what? Because if you are doing matrix multiplication, it's the first row times the first column, and if you have another column, then the first row will multiply another column, but then here we have only one column here. Okay, so what you do is we multiply the second row by the column, and you get to 0 times x1 0, and we have 1 times x2 plus, so you get x2 plus 1 times s3, thus you get s3, and this is equal to 6. Okay, now we multiply the last one, we get 0 x1 plus 0 x2, then get out x3 should be equal to what? 1. So from Gaussian elimination method, we've been able to reduce this whole equation, which was having values here for x1 and x2 everywhere. I've cut this part. Okay, look at this part off. We've been able to cut this part off. Okay, and now the equation is looking like a certain triangle. Okay, so how do I solve this if I have something like this? Okay, now with this, it means the last equation that you got from the reduction, if you could see the last equation that we got from the reduction, okay, from the last equation means x3 is what? Equal to 1 from the last equation here. If that is the case, we know from this equation x2 plus x3 is equal to 6, so it means x2 is equal to 6 minus x3, which implies that x2 is equal to what? 6 minus 1, that will give me what? 5. Okay, so from Gaussian elimination we are not doing anything big, but then we are still finding out x1 x2. Okay, now with x1 plus 2 x2, which is 5, plus 3 x3, which is 1, should give me 13. Okay, now with this x1 is equal to what? 13 minus 10 minus 3. Okay, and this means x1 is equal to what? 0. Alright, so from the equation we are saying that we're able to use Gaussian elimination to find for x1, x2, x3 being this. Okay, now with this, if you pick the first equation, x1 is 0, okay, x2 is what, 5, x3 is what, 1. What would this give us? We get 4, and this means this is true. Okay, for the second equation, x1 is what, 0, x2 is what, 5, x3 is what, 1, and we get what, 10 plus 3, which will give us 13, and that is true here. Okay, now s3 is what, s1 is 0, s3 is 1, and this will give me what, 1. I mean, this is also true. So it means that this solution here is true. We use what we call Gaussian elimination method to solve this, and this is very easy. When the reason why we are saying Gaussian elimination is very easy in using to solve systems of equations is when you have a system of equation whereby the unknowns are, let's say, 5, then you're going to suffer. Okay, so always try to understand this. Thank you, and don't forget to subscribe to my channel for more videos in the future. Okay.